CSIR NIST Trivandrum. I feel very proud to introduce this eminent scientist to you, friends. Dr. Chandran has received his PhD degree in the field of ferroelectric liquid crystal devices from CSIR National Physical Laboratory, New Delhi, and subsequently joined CSIR Central Electronic Engineering Research Institute, Pilani, as scientist in 2016. There, he worked in the area of advanced ceramic, that is LTCC based printed devices, and customized packing of micro electromechanical systems and microsensors for societal and strategic application. His current research areas are interface of liquid crystals with immiscible structures, ferroelectric liquid crystal based electro-optical memory devices and sensors, triboelectric nanogenerators, thick film screen printable devices, and so on. Dr. Chandran has authored more than 20 publications in reputed international journals and presented papers in various national and international conferences. He has several prestigious awards to his credit, including Early Career Research Award by DST in 2019, Foundation Day Award from CIRI in 2019, Young Scientist Award in 2017 by Venus International Research Foundation, Chennai, DART Fellowship in 2015, CSIR SRF Fellowship in 2014, and so on. He has completed 4 major projects funded by various agencies, and 2 projects are going on. Dr. Achu Chandran, in spite of his busy schedule, accepted our invitation and present here to share his valuable knowledge with us. I proudly welcome this young eminent scientist to this program. Cordial welcome to you, sir, because your presence makes us very, very happy. Finally, I extend a warm welcome to the faculty members, research scholars, and the students of various colleges and institutions who have joined this webinar program. Welcome, one and all. Thank you. Over to my Meera.
Thank you, ma'am. Thank you for your kind words. Now I hand over the mic to our honorable and respected Principal Madam, Dr. K.V. Jayashree, for the felicitation address. Please, ma'am. Welcome, ma'am. Hello.
Thank you, Meera.
Welcome, ma'am.
Can you hear me? Thank you, thank you. Namaste to all dear participants. Welcome all to this webinar on materials for space application organized by Department of Physics. The COVID-19 pandemic and the lockdown imposed from mid-March to contain the spread of coronavirus have made educational institutions go on digital platform to mitigate the loss of 3D learning. Education is a constantly field, and in order to ensure its continued growth, it is imperative that teachers also evolve alongside it. It has become a prerequisite in today's time for it to constantly refresh their knowledge in the current development of the subject. Every day, new discoveries or information about the world is provided to us, and it is the role of the teachers to introduce their students to all of these new phases. Knowledge upgrade is a must. The teaching community must make sure that it keeps itself abreast of all new developments and choose the path towards continuous learning and growth. Realizing this, we have arranged this webinar and the current trends in materials for device application for the benefit of the teaching fraternity. Let us keep in mind that dedicated educators are lifelong learners. Dear participants, let us continue our journey towards excellence by proving that Nothing can stop our learning process. That if there is a will, there is a way. Good luck to all participants and my dear teachers.
Thank you, madam. Thank you for your kind words. Now we are moving to the first lecture of the webinar series. I invite Dr. Achyuchandran sir for his presentation. Welcome, sir. Achyuchandran sir.
Thank you. Yeah, can you hear me?
Sir. Yeah, I can hear.
Okay, so very good morning to all of you. So before going to the session, I would like to thank the organizers of this event for giving us an opportunity to share our research view on materials to device applications in these difficult times. Okay, let me share the presentation now. Okay, is the presentation visible? Slides are visible or not?
Yes, sir. Yes, sir. It's visible and audible, sir. Clear.
Okay. Okay, let's start.
Aye.
So once again, welcome all to this webinar on materials to device applications. Here, I would like to present my topic like soft materials for device applications. Myself, Dr. Achyuchandran, working as scientist in functional materials section, material science and technology division of CSIR NIST, Trivandrum. Before going into the detail, let me introduce our institute, CSIR NIST. It is one of the constituent laboratories of Council of Scientific and Innovative Industrial Research, CSIR. We have 39 laboratories all over India. So CSIR NIST is one among which is located in the southern part of India. And we have 5 divisions spanning from agro-processing technology, chemical science and technology, environmental technology, material science and technology. Then we have microbial technology division. And coming to the outline of this talk, we will be seeing why we need soft materials. Then we'll be having a brief introduction on liquid crystal materials, then optical memory devices, LC-based biosensors. LC means liquid crystals. Then printed electronic devices, microheaters, flexible energy harvesters. So these are the different type of devices we are working on. And let me introduce you why we need soft materials, why we are more focusing on this type of materials. So if any interruption is happening in between the talk, you can communicate in between, and we can reconnect also. Because since it is a one-way communication, it will be difficult whether the audience are hearing what I am conveying and all. Okay. Hello. Hello.
Yes, sir, we can hear.
Okay.
Yes, sir.
Yes.
Actually, feedback is important because we are not seeing the faces of the participants, right? If it is a live talk, it is a different thing.
If any problem, we inform you, sir.
Yeah.
There is
If
any
any
problem,
interruption is happening, you can inform me. Okay, I'm just continuing. Soft materials, why it is important is because these are easily deformable by thermal stresses or thermal fluctuation at about room temperature. Because when we are applying any external stimulus, suppose temperature, then maybe electric field or magnetic field, soft materials can easily be deformed by these type of thermal stresses or any type of external stimuli. So we can utilize this deformation for any device applications. Based on the properties of materials, we can fine tune it for different applications, include display devices, sensors, then actuators and all. As you know, in display devices, liquid crystal displays are very famous, which are based on soft materials. They are called a liquid crystalline phase or liquid crystalline materials. They have unique mechanical, electrical, and optical properties. Then again, soft material family include polymers, colloids, foams, gel, granular materials, liquid crystals, and biological materials. So these together, this class of material together is called soft materials. Now we'll see the wonderful application of these materials, especially the liquid crystalline material. So before going into the introduction part, we can see the matter is classified into solid, liquid, and gas. In between the solid and liquid phase, we have the liquid crystalline phase. Solid is having anisotropic properties, and liquids are having isotropic properties. So liquid crystalline material is coming in between anisotropic solid and isotropic liquids. So this phase of material has been introduced by a German physicist Otto Lehmann and an Austrian botanist Friedrich Reinser in 1888. So they have first introduced this liquid crystal material. First material was, I think it is cholesterol benzoate. It's a cholesteric phase of liquid crystal. It has been invented from a carrot. Okay, these are naturally occurring materials. So typically a liquid crystal material have the following structure. It will be having a thread type structure as seen in the figure. And from a chemist's point of view, these are having rigid molecules in the center having flexible tails. From a physicist point of view, these are rod-shaped molecules. Again, another class of liquid crystal molecules are there, which is having disc shape and banana shape. But typically, we will be referring to the molecule which is of rod-shaped molecules. That is commonly used in our display devices. So we are more focusing on thermotropic liquid crystals. So why we are calling is thermotropic means the phase change of these materials will occur with change in temperature. So when you are cooling these materials, it will become solid phase, and when you heat it, it will become liquid. So in between these two states, we can have pneumatic, cholesteric, and cymatic phases with a different orientation of molecules. Pneumatic is the most simple form of liquid crystals. The word pneumatic came from a Greek word for thread. As you have seen in the earlier figure, these are thread type structures. These are having definite orientation order, but there is no positional order. So based on the order parameters, we can classify different hierarchy of liquid crystals. So these are the basic form of liquid crystal called pneumatic. Then coming to the cholesteric phase, this is a special case of pneumatic liquid crystals. These are chiral molecules. Okay, so in layer by layer, you can arrange this pneumatic molecule and get a cholesteric one. And coming to the cymatic phases, these are like layered structures of molecules. So there, the word cymatic came from the Greek word for soap. So we can see that in soap also we can have layers. One layer can slide over the another. That's the importance of these cymatic phases. In cymatic A phase, molecules are having average tilt of 0 degree with this perpendicular direction of director, and there will be a slight angle theta tilt in cymatic C phase. Okay. So when there is a tilt angle, it is cymatic C, and when there is the tilt angle is 0 from the director, then it will be cymatic A. And the speciality of these molecules are they are highly viscous. When you add a chiral molecule to this cymatic phase, it will show ferroelectricity. So chiral cymatic molecules shows ferroelectricity. So we are more interested in this ferroelectric class of liquid crystals. Now coming to the ferroelectric liquid crystals, as I told, when we add a chiral molecule to this cymatic phase, it exhibits ferroelectricity. And how this ferroelectricity is coming, it is because of lowering of symmetry. Because of lowering of symmetry, it will exhibit a spontaneous polarization, and you know that if there is an effective polarization over the volume, then we can have the ferroelectricity in these type of molecules. So C2H is having twofold symmetric axis and one mirror plane and one center of inversion. That's called a C2H symmetry. And when we are adding a chiral molecule, this C2H symmetry will reduce to C2. Okay, then the molecule become chiral cymatic phase. It is represented in SMC star. And the first molecule of this kind has been invented in DOBM BC. It is called P-D-cycloxybenzidine, P-amine to methyl butyl cinnamide. This is the first kind of ferroelectric liquid crystal molecule which has been invented in 1975 by Robert Mayer. So these type of molecules has been introduced in 1975 only. As you have seen in earlier, in 1888, liquid crystalline phase has been invented. Almost after 100 years, ferroelectric liquid crystals came into picture. And now it's revolving, and we can see that for the last 3 to 4 decades, if you consider the display industry, more than 70% of display industry is being handled by LCD type of displays. Now LED and AMOLED is coming up, but still they need, if you are using a backlight as LED, they need LCD, okay, for switching applications. But in case of AMOLED, it is not required, but you cannot make a large area panel by using AMOLED, and the stability of these organic molecules are very less. So that's how the liquid crystal displays are still important at present days. And if you can alter the properties of current liquid crystals, and if you can achieve a better viewing angle and a fast response, it will create a next generation of display devices by using liquid crystals. So now coming to the fabrication steps of liquid crystalline samples. So these are the basic steps which we need to follow to make a device based on liquid crystals. A fundamental step is photolithography. Then we have to do etching, then surface treatment of LC alignment, and then assembling and sealing. So let me tell what photolithography means. It's a common term. You might have been familiar about photolithography. It's transferring of a pattern or a desired pattern from a mask to your substrate. Here we are taking ITO coated glass plates as the substrate material. ITO is indium tin oxide. Okay, why we are selecting ITO is basically a transparent material and also conducting. Okay, so we need transparency and conductivity for use this type of material in device applications. You have to apply an electric field to alter the alignment of molecule, and you have to decide whether light has to be passed or not by using this alteration. And since we are using light, we need a transmission through these films. That's why we are focusing on ITO type of molecules. Rather than ITO, people are using FTO also, and also some composites of zinc oxide and all. And recently, graphene type of molecules with a single layer graphene, you can achieve almost 70 to 80% of transparency and all. So those will be very useful for flexible display type of things. The display device what we are making can be rolled if you are using graphene and all. Okay, coming back to the photolithography. Here we'll be using a photo mask. Then after placing this photo mask over ITO, you will expose it using UV irradiation, and you can transfer this pattern by using etching out the outside ITO. Then you will get this type of pattern at the end. Okay, you will be having steps like photoresist will be coated by using this spin coater. Then afterwards you will be exposing to UV. Then you will be soft baking it, and after exposure you can etch the remaining portions. And while cleaning this photoresist which is remaining in the center portion, you will get patterned ITO on this glass plate. Then coming to the surface treatment, why alignment is more important? Let me see. If molecules are being spread over this, it will be randomly oriented. So before filling the liquid crystal molecules inside these ITO coated glass plates, what we need is we have to give a pre-surface treatment. So mainly we are giving two types of surface treatment. One is homogeneous and other is homeotropic. And typically you can see that this will be the orientation of the totally assembled liquid crystal cell. We will be having two ITO coated glass plate which will be having a spacing. A spacer of normally 3 microns will be used, and in between these two glass plates you can fill the material by using capillary action. And you will be having a polymer layer here for giving this homogeneous alignment to these molecules. And if you need a homeotropic alignment, you have to use xylene type of surface treatment, which will be having perpendicular type of molecular orientations. So normally we prefer homogeneous type of alignment in these type of molecules. Again, you can make a contact on this ITO by using indium ingots. So typically, after assembling and sealing, the molecules are properly aligned and the whole device will be looking like this. Now I can show some prototypes which we have used for different type of studies. When we have studied the interface of these ferroelectric liquid crystals with different immiscible structures like air, water, and different engineering surfaces and nanostructures, we have made different type of geometrical arrangement of these type of liquid crystal cells. Here you can see that we have 8x8 array, means it's a type of a matrix type of arrangement, and each pixel, we can see that these are the pixels, and each pixels can be controlled by using individual electrodes. So there will be a combination of 8x8 matrix, and this will be useful for studying FLC and air. You can fill liquid crystal material maybe halfway, and the halfway will be air, and at interface how molecules are aligned, what will be the properties that we can study by using this type of cell arrangement. This has been published in Soft Matter, one of the reputed journals in soft materials. Then this type of geometry we have used there. And in case of FLC water interface, we have used a device structure like this. Here from one side you can enter this ferroelectric liquid crystal molecules, and halfway you can fill it, and from one side you can fill water, and it will create an interface at the middle part, and you can find individually what is happening at FLC water interface, FLC alone, and to water. So you will be having 3 parts in these devices. So the studies and the results we published in this Physical Review E, and it's from American Physical Society. It's a reputed journal, and here we found that near to FLC water interface, molecules of liquid crystals has reoriented, and from homeotropic type of arrangement it becomes homogeneous based on the tuning of surface energy and the interfacial energy. There was an interplay between the surface energy and interfacial energy. So I'm not going into the more details of this type of interfacial studies. Just we will be having how these are useful in device applications. Okay, then in case of FLC engineering surfaces, we have seen that how we can create engineered surfaces on this ITO. Here we have used a laser for etching the surface and created a periodic pattern on the surface, and we have created 2 ITO strips and find how LCs are orienting over ITO and on engineering surfaces. So we got 3 type of alignment. Over ITO, molecules were standing perpendicular. Over mylar spacer, molecules were parallel, and in between these 2 there was a transition from perpendicular to parallel. And in case of FLC nanostructures, we have created this type of molecular arrangement. Here in one side we can fill a pure liquid crystalline molecule, and in the other side we can create a composite or mixture type of molecule where we can incorporate nanostructure molecules to FLCs. Now, why we need to use this nanostructure is here when you are adding some nano compounds or like nano materials, nano wires or nano spheres or different geometries of nanomaterials which is less than 100 nanometer in range. Here what we have seen is the electro-optical and dielectric properties of the host material has been altered and has been improved in comparison to the pristine one. That's how it's a new avenue where you can tune the properties of liquid crystals by adding different size and shapes of nanomaterials. So that's the advantage of FLC nanoscience. Now coming to the characterization techniques which is available with us, the primary thing which we need to use is an optical microscope. Here, in order to see the alignment of molecules, you have to use a polarizing optical microscope which is integrated with a software, and there should be a CCD camera over this. And through an optical microscopy, you can have birefringence variation studies, tilt angle measurements, analysis of planar and vertical alignment, and optical memory. can study all these parameters of a liquid crystal material by using optical microscopy. And in order to study the dielectric properties, you have to use an impedance analyzer. So impedance analyzer is nothing but an instrument which will study the variation of dielectric permittivity of a material with various frequencies. You can see the frequency in x-axis, and you can find the corresponding impedance or permittivity on the y-axis. That's how we can characterize different type of molecular relaxed sections occurring in these molecules and how permittivity is being varied and all. So that's the beauty of this type of dielectric spectroscopic instrument. Here, when you are using a dielectric spectroscopic instrument, you can have the characteristics of the memory behavior of FLCs, then how relaxation is occurring in this type of molecule, how phase transition is occurring, and all these type of things and these informations can be gathered by using an impedance analyzer. And in order to characterize the other properties like spontaneous polarization, rotational viscosity, and like switching time and all, you need a material automatic liquid crystal tester, ALCT, material parameter measurement. And in order to find the orientational order and in which phase your FLC molecules are, you can use a small angle X-ray scattering. So through a small angle X-ray scattering measurement, which is called SATS, it's you can find what's the intermolecular spacing and how layers are being arranged, what is intermolecular or interlayer spacing. All those informations can be gathered by using a small angle X-ray scattering equipment. It's similar to our powder XRD, but having a different type of orientation. In powder XRD, you will be getting an intensity versus angle graph. Here, the distribution of intensities can be mapped in a 2D and 3D type of things in small angle X-ray scattering. Moreover, we are using very small angles, varying from some 2 to 3 degree to maybe approximately up to 30 degree in SAX. Then coming to the contact angle measurements, here you have we have used different type of contact angle measuring equipments for finding the surface energy of different molecules and also different films, different substrates and all. So basically, if you have dielectric spectroscope and optical microscope, you can do the characterization of electro-optical devices based on liquid crystals. Now, coming to the application of liquid crystals, especially the ferroelectric liquid crystals, here we would like to introduce a new effect rather than a display device. It's called an optical memory device. So how we can use the conventional display device by incorporating FLCs and nanocomposites, how we can convert it to an optical memory device, that we will be discussing in this session. So before going into this, let me explain you what an optical memory is. You people are aware that memory is nothing but a retaining of some information. Okay, if you can recall some information, some figures, some pictures, it's normally called memory. People are having memory and all like that, we can call. In case of this type of soft materials, the memory behavior, especially the optical memory, is retention of stressed state even after the removal of external bias. Okay. The external bias is something like if you want to or if you want to switch on a display, you have to apply an electric field. When you are applying an electric field, molecules will be oriented along with the electric field and you can have a switching of light and dark states. Okay, so even after the removal of external field, if your molecules are retaining in the stressed state, it is called memory. Okay. So we have seen that while incorporating some certain amount and a certain type of nanomaterials to the ferroelectric liquid crystal host, we can have this type of memory devices. Okay, the application of these memory devices is nothing but you can apply some bias, you can remove the bias, your display will be on and display will be running without any power consumption for a certain duration, and that duration is called memory. So I will explain how we have fabricated this soft memory device or optical memory device by using liquid crystals. What we have done is we have maintained the cell gap of 3 micrometer. The host material, FLC material, what we have used is ZLI 3654 It's a commercially available ferroelectric liquid crystal material, and this is the phase sequence of this material. If you go below minus 30 degree, material will become crystalline, and if you go above 86, it will become isotropic phase. And in between these minus 30 to 86, it will be exiting a liquid crystalline phase. And up to 62 degree, it is in ferroelectric liquid crystal phase, schematic C star. Okay, it's a very broad range. Almost a 90 degree it is covering. Okay. And at room temperature, you can see that these molecules are in deep schematic C star phase. So when we are adding nickel oxide nanorods into this FLC, it is exhibiting memory. These are the nickel oxide nanomaterials, its characteristics. We have made these nickel nanorods of almost 20 nanometer width and diameter of 20 nanometer length and diameter of 5 to 6 nanometer. And intermolecular spacing in this spacing of this nanomaterial was something around 0.22 nanometer from each atom, and these are the excited pattern. And after a two analysis, we found that it's having 111 phase. Okay, this 111 phase is something like a dipolar type of thing in nano nickel oxide. So we have prepared 4 different samples. One is of pure FLC, and in other 3 we have added different concentration of nanomaterials, 0.25, 0.5 and 1 weight percentage. And these are the dark states and these are the bright states corresponding to those display devices. In case of pure FLC, you can see that the dark space is dark state is not completely dark. There is a lot of disturbance in this alignment. Molecules are not properly aligned, and a lot of defects are being incorporated in this dark phase. And while in increasing the dopant concentration from 0.258% to 1 weight percentage, we found that at 0.5 weight percentage, we got an improved alignment. Means dark state is comparatively more darker comparing to all other dark states, and the bright state is almost defect free. So we further chosen this concentration as the optimal one for this optical memory device, and we compared the electro-optical and parameters of FLCs and other dielectric parameters of FLCs for this 0.58% and the pristine one. So further, we have characterized by using dielectric spectroscopy and polarizing optical microscopy. Here, we found that in case of pure FLC material, this is the tilt angle versus applied voltage. When you are applying a bias at around 8 volt only, the molecules are switched completely. When the molecule will be completely switched, we will be getting maximum tilt angle. So the tilt angle corresponding to these molecules are coming around 22, and when you have applied 8 volt, then only all the molecules are switched. But in case of this composite, where we have added 0.58% of nano nickel oxide, at 4 volt itself, the molecules has been switched. That means in order to switch your mixture, you need to have only 4 volt rather than 8 volt. Okay, so almost 50% reduction in power consumption can be achieved if same current is being flowed for these switching applications. So your mixture, while incorporating nanomaterial, has shown a lowering of triggering voltage or threshold voltage, which saves a lot of energy in case of switching applications. So you need to have almost half the electricity which is required for the pure material for your composite one to switch. And once you switch, you have to remove the bias and check whether your molecules in this mixture is exhibiting memory or not. Here you have applied 0 volt, that means it is in dark state. You have applied a 15 volt bias and switched it to bright state, and just after that you remove the bias. And up to 20 minutes, this is for 1 minute 10 seconds after removal, then 1 minute after removal, and up to 10 minutes after removal. So these 3 states are still in bright, and after 20 minutes only it is going back to the scattered state. So up to 20-minute time duration, your device is in switch state, which is showing optical memory. So that's the beauty of your device. Up to 20 minutes, there is no requirement of any power. Only you need to trigger it at the initial stage, and after that you can remove the bias. Okay, this has been further verified through different characterization techniques like dielectric spectroscopy and optical response. Here in dielectric spectroscopy, you can see that the variation of dielectric permittivity with the various frequencies for pure material and for this composite materials. So when you are applying 0 volt, means there is no bias. In this case, there is no external DC bias. In that case, your dielectric response is like this. The real part of permittivity is varying like this. When you are applying a 15-volt DC as an external power, the complete molecules are being switched to one direction. So the permittivity has come down, and you removed the bias for this pure one, and almost after 1 minute, it has been retained to the previous state. So the memory duration is very less in case of pure material, only up to 1 minute. But in case of your composite sample, you can see that the memory behavior is up to 10 minutes. You switched it, and up to 10 minutes it took to return to its previous state. And again, by using optical response, you can see that in case of pure material, when you applied a time delayed square pulse, you can see that this is the response towards this time delayed square pulse. So when your molecules are in positive bias and in negative bias state, you can see that the output of this pure material is simply following the input signal. That means there is no memory, there is no retention of information in this case. In case of your composite sample, you can see that this is the input pulse and this is the output pulse. When your input is being switched from 1 to 0 state, the output is still remaining in one state till another reverse pulse. So up to this one state, this time duration is the memory duration of this type of molecules. And in negative cycle, the memory is little distorted due to the small alignment and other issues in these molecules. But in this positive cycle, almost the memory is being retained for every cycles. So from optical response and from dielectric spectra, as well as from PM microscopic images, we have concluded that these molecules are having optical memory. Then how this memory effect is only happening in case of mixtures, not coming into the pristine one. So further we investigated those things, and we have seen that in case of the pure material, when we have taken the dielectric relaxation spectra, we have found that there is an ionic peak which is coming along with the Goldstone mode peak. This is the characteristic peak of liquid crystal molecule. Goldstone peak is the characteristic peak where azimuthal angle rotation is there. But in case of ionic peak, this is an additional peak which is coming due to the presence of ions in your pure material. But in case of your composite material, this ionic peak has been disappeared. Only you are having this characteristic peak of FLC. That means by incorporation of nanomaterials, some sort of screening effect has been introduced to this ionic peak. So somehow ions are getting trapped by using these nanomaterials. So what will be the mechanism? In order to elucidate it much more, we have checked for the conductivity of pure sample and also this dispersed sample. In case of pure sample, the conductivity is very high, and the conductivity is mainly contributed from this ionic peak, because most of the FLC molecules are insulators, and the conductivity is only because of the impurity ion contained in this material. So in case of this composite sample, we found that the conductivity is less comparing to the pristine one. That means the ions are not that free to conduct the electricity. So we have elucidated a model from these observations, and we found that because of trapping of impurity ions onto the surface of nanomaterial, these are the nanomaterials, this blue color is FLC molecule, and red and green are impurity ions. So when you are switching it, these impurity ions will be traveling to the opposite electrodes, and while traveling to opposite electrodes, it may get trapped on the unsaturated surface side of nickel nanorods. Because of that, there will be an effective reduction in depolarization field, and this depolarization field cannot revert back these FLC molecules when bias is being applied. So because of this reduction in depolarization field, because of trapping of molecules, there will be effectively a memory for these molecules. Means when the molecules are switched, there is no depolarization field when you remove it. So the molecule can have a tendency to remain on those state for a particular duration. Okay, if depolarization field is present there, then this molecule has to come back. So if you reduce the depolarization field by this type of mechanism, the molecules can exhibit, FLC molecule can exhibit memory. That's how memory is being imparted in this type of FLC nanocomposites. So this is a wonderful device. The application will be like you will be having a display device. Suppose in a remote area there is a scarcity of electricity and all. Then if you have such type of display device, you only need to trigger the display by using an electric field to switch it on, and afterwards you can remove it, and that switching time is in millisecond range. If you remove the bias, the molecules will be on molecules will retain for a longer duration because of this memory effect, and the information will be displayed for that memory duration. So suppose if these molecules are being used, means up to 20 minutes you are getting the memory. In that case, what happens is up to 20 minutes, there is no need of any external bias. So information can be displayed up to 20 minutes. So it will be useful in your e-book readers, something like Kindle type of devices, where you may take up to 20 minutes to read one page. Or in between, if you have to skip the information, you can apply a negative bias. Then the next page will be coming after a refresh. So in order to refresh, you can apply always a reverse bias, and up to the memory duration, the molecule will be retaining the stressed state. That's how the memory is being imparted in this type of FLC based nanocomposites. Now coming to the second device, which is liquid crystal based biosensors. Okay, so liquid crystal based biosensors are more important in nowadays because of this easy diagnosis and all. Now we'll be seeing how this type of molecules is showing biosensing things. Biosensing is nothing but if your molecules are responding to the external environment where this biomolecule or bioactivity is there, and you can detect it through some variation parameters of these molecules. Something like what I told earlier, molecule can have a homeotropic alignment where it can be standing perpendicular to your substrate. So we have given some saline treatment for a pure FLC type of cell where molecules are standing perpendicular. In that case, no light will come out. Okay, there will be a complete dark state if all the molecules are being in perpendicular to the substrate. It is because of the birefringence of the molecules. Because these FLCs are birefringent, we will be having E ray and O ray. E ray is something like extraordinary one, and O ray is ordinary rays. So when these molecules are being splitted, what happens is after coming out of these molecules, it has to be contained, and there will be no light passing through these FLCs when it is in homeotropic case. But when it is in homogeneous case, there will be effective light coming to this. So we'll be exploiting this property for sensing biomolecules in the vicinity of liquid crystals. Here in this scheme, we have seen that when we incorporated some cholesterol oxide enzymes along with cholesterol, here we have seen that the molecules in perpendicular state has been changed to parallel state, and it has been characterized through an effective transfer of light through these molecules. It will be more clear if I show these optical pictures. Here, this is a pure FLC cell it's not FLC, it's a pneumatic liquid crystal 5CB. It's a pneumatic liquid crystalline cell in homeotropic alignment, means molecules are aligned perpendicular to the substrate. So when some enzymes are being added, there is a small disruption in molecular alignment. Then you have added different concentration of cholesterol into it. So the concentration of cholesterol, if it is 10 milligram per deciliter, you can see that molecules are slowly varying from homeotropic alignment to homogeneous, and beautiful colors are appearing with increase in concentration. Have varied the concentration from 10, 50, 150 and up to 250. 10, then 50, 150 and 250. So while increasing the concentration of cholesterol molecule, you have seen that there is a homogeneous alignment. Means from perpendicular state your molecules are slowly getting tilted, and completely it is getting tilted and appearing very beautiful colors in higher concentration. So normally for a healthy man the cholesterol concentration is coming around 120 milligram per deciliter, and we can easily characterize those samples by using this technique. And now we want to know how this alignment change is happening by incorporation of cholesterol, and really what is the driving energy behind this. So in order to that, we found that when we adding a cholesterol molecule in presence of cholesterol oxidase, it's an enzyme. This enzyme, cholesterol in presence of this enzyme and oxygen will become cholesterol and hydrogen peroxide. And as you know, hydrogen peroxide is a gas which will be trapping in this self-assembled monolayer and may create small nanocups type of structures. And if you add more cholesterol, there will be more hydrogen peroxide. And if more hydrogen peroxide is there, with varying the concentration, the pore size will be very high. And if pore size is very high, there will be more disruption of your molecular alignment. So it's a simple mechanism through which you can alter the variation, or you can study the variation of pore size by having more number of hydrogen peroxide, which is proportional to the concentration of cholesterol. That's how you can sense the molecular alignment. Okay, it's corresponding to all these things. The first one is having very small nanopores like this. And when you vary the concentration from 10 to 250, 10, then 50, 150 and 250, there is a rigorous change in hydrogen peroxide concentration, and surface is very rough in case of this one. So if the surface is rough, means the molecular surface energy is very high and it holds the molecules towards the surface, and it's become homogeneous compared to the homeotropic type of thing. And here we have quantified the light passing through this. We have quantified the light passing through this by using a spectrometer, and we found that the intensity of light is getting higher with the concentration of cholesterol. It's a linear thing. So if you have an unknown sample where you don't know the concentration of this molecule, you can just to find the intensity of light passing, and you can correspond those intensities. Suppose it is something like coming around 1350, then you can find what will be the concentration of cholesterol by simply drawing a line, because this is a linear varying type of graph. So somehow it can be used for qualitative and quantitative type of alignment or analysis for this cholesterol. So different from cholesterol, you can use different type of antigen antibodies, or maybe different type of RNAs at all. So it's a new type of mechanic, and the detection is very rapid in case of LC biosensing scheme. Also brief about LC biosensing. Now we have seen how liquid crystal molecules has been used for optical memory, biosensing applications, and for conventional displays and all. Now we are moving to a different session. Apart from liquid crystals, we are also actively involved in printed electronic devices. Okay, so printed electronics is nothing but you will be having suitable materials and substrate where the devices can be printed on your substrate by using screen printing, inkjet printing, or any other state-of-the-art techniques, something like lithography and all. So we are more concentrating on screen printing type of devices, So first one is liquid, this LTCC. LTCC is nothing but low temperature co-fired ceramics. It's an advanced type of ceramic structures, LTCC based micro hot plates. You know, hot plates are nothing but when you are applying some voltage, it will generate heat through electro heating mechanisms. And interestingly, in case of micro hot plates, the power consumption is very less. You know that in daily applications you are using iron box. Okay, iron box is also a hot plate, or maybe a heater type of thing, or a convectors and all those things. All those are working similar to these joule heating mechanisms where electro heating is happening. So in an iron box, you need minimum 750 watts to 1000 watts for getting a temperature of 150 to 200 degrees Celsius. But in case of micro hot plates, where we are using this printed electronic mechanism or screen printing, here you can see that these are the various versions of hot plates available with us. And here we can see that by using less than 1 watt, means 0.9 watt, we can attain a temperature of 300 degrees Celsius in 3 by 3 mm range by using printed electronic mechanisms. Here you are having this as LTCC substrate. Okay, our LTCC substrate, these are LTCC substrates. Whatever you are seeing in blue color is stacked LTCC substrate after firing. Here you can print the heaters, okay, through different designs, and you can fine tune the temperature and also the power consumption by trimming the resistance and all. So this is a meander type of design, is a version 1. Here I am showing 4 versions. So here the size is 5 by 5, and with a power consumption of 2.5, it can reach up to 300 degrees Celsius. While coming to this version 2, where the size is little higher and have this type of assembly type of slots, here by using 2 watt power, you can attain 300 degree. And again, a spiral design where you can use 300 degree by using a 2 watt power consumption. So the latest version, which is called LTIVA, which is the most efficient one, what we have seen till now is nothing but LTCC with interconnects through vertical axis based one. So this is a technology brief. The thing is, like, these hot plates are very rugged, reliable, and having novel interconnects with high temperature and mechanical stability. So if you apply 2 volt, it can reach up to 250. Okay, with very less power consumption, maybe 0.5 ampere and all. So in case of these devices, these are eco-compatible and ROHS compliant materials are used. So it's eco-friendly, low cost, portable device. It has been used in strategic as well as domestic application. We have developed these devices for a particular project for DRDO. There you need to heat a closed chamber for microforming type of concept. Okay, microforming I will explain in the next slides. So this one, you have to use different types of hot plates in a closed chamber. There, this DRDO people used to do microforming in a closed container, because especially in cold deserts like Leh Ladakh and all, or maybe in Kargil and those regions, they need to have fresh vegetables. Okay, currently what they are getting is packed foods. The soldiers or Indian Army Jawans are getting packed food, and continuously eating of this packed food is not good for their health. So DRDO has developed a technique called microforming. They're using some heating or closed heating arrangement. They can grow green vegetables in almara type of structures. Okay, simply you can imagine like you have an almara at this cold place, and which is equipped with these type of heaters, and your outside environment temperature is -3 degrees Celsius. But in order to germinate, or if the seed need to grow, you need an ambient temperature of 15 to 20 degrees Celsius. Otherwise, germination will not happen. So by using micro hot plates, what we have done for DRDO is we have regulated the temperature of these closed almaras. These are closed almaras at around 20 degrees Celsius by using less than 100 watt power consumption. 100 watt is nothing but if you need to buy switch a bulb, it need minimum 100 watts. An incandescent lamp will consume 100 watts. A fan will be consuming around 60 to 70 watts, maybe up to 100 watts also. So by using that much power itself, a whole Almara type of arrangement can be heated up, and that can be used for microfarming type of arrangements. We have installed this type of almaras, or you can see it as micro farming arrangement in Leh Ladakh at two different places. And that place was extremely at a high altitude, 17,000 to 18,000 feet above sea level. That was Changla Pass, and other was in Leh Ladakh. So we went there and have installed this center at Defense Institute of High Altitude Research, DRDO Tihar at Leh. So it's one of the highest terrestrial research station, and because of this height, it has been well reputed by Guinness Records, because this is the highest altitude research station in the entire world. So they are facing these temperature difficulties. For different applications, they require this type of hot plate, and one such application is microfarming, and others something like warming of liquids, melting of butters, slicing, and all those applications. So this is one such regulations what we have done. So you can see that the outside temperature is -3, and inside chamber it is 20 degree, which has been regulated through these micro hot plates. Now we'll be seeing some other type of printed device. It's called thick film electrodes for sensing applications. Again, it was a project for DRDO DRD at Gwalior. They are working on biosensors, especially for detection of dengue type of things. There they need different electrodes for electrochemical sensing applications. So we have designed a different type of thick film electrodes on alumina and low temperature coated ceramic substrates, and we have custom developed such type of electrodes for thick film sensing applications. So here these are three electrode systems. We'll be having a reference electrode, working electrode, and a counter electrodes. Okay. So for biosensing application also, we can make these type of customized substrates. These are also interesting devices. Over this substrate, you can immobilize your biomolecule, and you can have a detection through taking contacts towards this electrochemical impedance analyzers. You can study the variation of current when the different concentration of biomolecules are present in your droplets of cells. And another activity which we were involved is the customized packaging of MEMS and microsensors. MEMS is nothing but micro electromechanical systems. These type of systems are very much used in launch vehicles and for gas sensing applications, field effect transistors, pressure sensors, and for making sensor modules with application specific IC integrations. So here, these are the sensors which has been made on chips, and these chips are basically based on silicon. Okay, but the problem is that the pad size, the electrical contact pads, are of micrometer size. So in order to handle these micro contacts towards an external circuit, you need to have a casing type of arrangement through which you can take contacts through external leads. And that's how we are making customized packaging for such type of microsensors and MEMS devices. Here these are FETs. FETs are something like these are extended gate type of thing, and here field effect transistors of different films has been made at series, and we have packaged it through this customized alumina packaging thing, so that whatever molecules are coming here can be sensed through the electrical connections. Basically, this type of ISFET and IGFET are used for pH sensing mechanisms. And gas sensors can be packed by this type of arrangement. Through this LTCC ports, gas can go inside, your sensor can be placed inside this cavity, and the connections can be taken through these leads. These are various inertial sensors which has been designed for ISRO. These are inertial sensors, something like gyroscope, accelerometers, and all. So this has been packed by using customized packaging, so your security is being protected. Here we have used die bonding and wire bonding, which are one of the popular technique for fabrication of sensors. Here pressure sensors has been made and silicon substrate and has been integrated with this LTCC type of arrangement, and this has been used by IG car and all. So this defense and as well as this atomic energy agencies, they are using these type of pressure sensors. And a complete pressure sensor module with integrated electronics printed on a single application specific IC with proper integration has been done by using this type of arrangement sensing. So whatever flow, the flow pressure you have to sense, you can connect through this needle, and sensor is here. Okay, the gas will flow through this. You can find absolute and relative pressures by using proper integrated electronics. So this will be acting as a chip. Directly you can place and you can find it. So this is about printed electronic devices. And at present, we are focusing on flexible energy harvesters also. This is one of the upcoming domain where rather than the conventional energy sources, it can trap whatever energy available in your environment. Like in order to tap the sunlight, we are having solar cells. It's a renewable energy source. In order to tap the energy from wind, we have wind farms using these wind turbines. In a similar way, in order to tackle the mechanical energy, we can use an interesting type of device called triboelectric nanogenerators. These devices has been introduced by a Professor Wang in 2012 at Georgia Tech, USA. So it has been invented in 2012 only. Since we know that triboelectric effect, the contact electrification process, is well known from centuries. But in order to tap those energy in the form of a generator, we have to wait till 2012. So that was a longer period, and through this Wang and team, they found that this mechanical energy can be harvested by using contact electrification and electrostatic induction. Basically, we are having two dielectric materials in this device structure. Is a triboelectrically active material, 1 and 2, having a spacing in between them, and we have two electrodes on the other side of this dielectric material and a casing. So when these materials are coming in contact, there will be effective exchange of charge in between these two molecules because of the difference in electrostatic potential of these molecules. And when these molecules get separated, what happens is, in order to compensate this charge transfer, there will be electrostatic induction on these electrodes in the counterparts. So these electrodes will be having some voltage on the surface, and that can be used as a current through an external connection. So for every action, means when this dielectric material is coming in contact with the other one through a pressing and a releasing cycle. So for every pressing and releasing cycle, there will be an energy output. So this mechanism can tap energy or mechanical energy which is available in your environment. So for an example, something like if this nano generator can be made into a very small size which can be incorporated along the diaphragm of a person, suppose. So you know that in order to drive a heart, you need a pacemaker. Okay. For a normal person, pacemakers are there inbuilt by birth, and artificially pacemakers has battery power, and that has been incorporated through surgery, and the battery is of 5 to 10 years warranty or not. The thing is, like, after 5 years, you have to replace those batteries since it may drain out. But your heartbeat is a constant mechanical motion. There is a constant mechanical continuous motion along with this respiration action where diaphragm is moving. If you can incorporate such type of small sensors to this diaphragm, continuously you can supply energy to your heart and you can replace the batteries of your pacemakers. So that's the beauty of this device in micro level. And in mega scale, if you have some energy harvesters, something like sea, where continuously your ocean tides are there, and that tides are continuous. And if we can make a mega scale type of this device there and place in front of those mechanical waves, we can continuously generate this type of contact electrification and separation type of mechanism and get an electric output there. So the main advantage of this technique is it's very cheap, because the material what we are using here is of positive and negative triboelectric series materials are very cheap and readily available. Something like air, skin, leather, then asbestos, glass, mica, quartz, nylon, etc. And negative side, you are using Teflon, then PVC. So these are readily available type of material. And if the triboelectric series or gap is very high, if you take a material from top positive and the top negative one, the energy output will be very high. So such type of device will find applications in pacemakers, Bluetooth devices, MEMS-based microsensors, and actuators. And the power efficiency or power conversion efficiency has been reached up to 85% till date. And the power output is coming around milliwatts to watts nowadays. So comparing to your conventional piezoelectric nanogenerators, this is almost having 1,000 times power efficiency and power conversion things. So this is the beauty of triboelectric nanogenerators. This is one of the field that now we are working on. And now we can wind up the talk. And if you have any queries, you can ask. So we have seen different devices based on materials which are readily available, and also which has been synthesized in the lab. Something for optical memory applications, biosensing applications, and for printed electronic things, micro heaters, and flexible energy harvesters. Thank you all for listening. If you have anything to discuss, we can have an interactive session.
Hello, Dr. Meera. Hello, Dr. Meera.
Hello. Yes, yes.
Dr.
Thank you.
Achikadrin's speaker was over. Okay.
Participants, if you want to ask question, please ask your questions by unmuting your audio. Please ask question. If anybody want to ask question, please ask. Or write your questions on the chat box. Can you hear me?
Okay, it's clear. But I think the participants cannot able to reach your point there. There is some technical problems. So better to ask the...
Yeah.
Pardon, Meera?
Yeah. They are joining. I send the link again.
Hello, Dr. Achu sir. Can you hear?
You,
Hello, sir.
Yeah, I can hear. Yeah.
Sir, you have clearly explained.
No
Hello.
Yeah.
Meera, excuse me.
Pramila ma'am, tell me.
Okay.
Yeah.
Dr. Achu sir, you have clearly explained about liquid crystals, liquid crystal biosensors, and printed electronic devices in a very wonderful manner, so that all these informations are very useful for our new research scholars, and I hope all of them are much benefited by this talk. I have one doubt, sir.
Yeah, please ask.
Sir, what about the thermal properties of these liquid crystals compared to the solid crystals? Thermal, you have mentioned all other properties. What about the thermal properties?
Yeah. Actually, these are, as I told earlier, the classification itself is based on the thermal properties. Something like thermotropic liquid crystal. The word came itself related to the temperature. If you vary the temperature from room temperature to a higher temperature range, you can get different phases of this material. So basically, if you vary the temperature, phase transition will occur in case of liquid crystalline molecules. Okay, these are thermally responsive molecules.
Sorry, all these methods are applicable in our ordinary lab, in our ordinary college situations?
Some of the things or the characterization things are little costly and sophisticated instrumentation may be required. But for ordinary type of things, maybe by investing around 5 to 10 lakhs, you can set up a liquid crystal lab for
Okay,
regular type of
okay,
characterization thing. And if
okay.
you have those setups, you can contact with any of the CSIR lab for characterization facilities. We are open to all type of students. So through a small charging of amount, we can characterize your samples at your institute. It's
Okay, okay.
also common for all CSIR labs. So most of the
Uh,
facilities are now commonly available for public.
Sir, what about the NLO property, sir? That is usually when we do this one research in solid materials, NLO properties we have to depend on IISc Bangalore. We have to get the
Which
permission. NLO,
which
non-linear,
property?
non-linear
Non-linear optic.
optical property, sir.
Okay. Actually, currently we don't have a non-linear setup, but it is being applicable in other CSR labs, like something in National Physical Laboratory, where from I have done my PhD. There, non-linear optical facilities are available because they are
Okay.
working on these solid crystals, something like quartz and all. So they
Yeah,
are growing
yeah.
it. Crystal growth facilities also available there. And I can
Okay.
share the contacts. You can drop me a mail. I can share the contacts of those persons that are working on these non-linear systems there. And
Okay.
also you can find something in ISIS and IITs nearby.
Okay. Sir, is there any funding agencies to start such a research lab in our ordinary colleges?
Yeah. UGC is giving some startups to the young faculties, and
Okay.
DST is giving early career award or startup research grant to the faculties who are with government and private colleges. And
Okay.
there are a lot of other collaborative funding schemes available
Okay.
with
Okay.
all these government agencies. So that can be explored.
Okay. Thank you so much, sir. Over to Meera. Meera? Hello? Hello, Meera?
There are two questions from the participants,
Yeah,
sir.
please.
Hello.
Yeah, hello.
Which type of material is used for tank?
Okay.
It's a question from Ashwati Manu.
Okay, so
Which type of material is suitable for tank?
yeah, can you see my slide now? Triboelectric generator. Yeah.
Yeah. Yes, sir. Yes, sir.
Here we have a triboelectric series where we have to take one material as a positive triboelectric one and the other as a negative triboelectric one. So for positive triboelectric type of thing, you can take quartz, nylon, wool, silk, alumina, or glass, any type of such materials which can retain a positive charge, and a combination with a negative one which is based on polyester, brass, copper, nickel, latex, or Teflon. So this series is available with a lot of journals and all. You can just Google it and find which is positive triboelectric and which is negative triboelectric. So you can make a wonderful choice between these two and make your own device based on time.
Okay, another question,
Yeah.
sir. What are the importance of biosensors in medical application? The question by Dibuna Abhiraj.
Medical application itself,
What are
now you can see that the present scenario, the COVID-19, there what we are using is RT-PCR based, means PCR means something like amplification of this your RNA. That type of testing is being used. So instead of it is a time-taking process. Okay, if you have a rapid diagnostic kit based on your antibodies, you can have a quick response. Maybe within minutes, you can find you are COVID positive or negative. So that's the importance of biosensors. Simply, the biosensors can be classified in three different types. One is basically based on your enzymes. One is based on antigen antibody reaction, and the third one is based on RNA DNA amplification sites. Okay, so the faster one is based on antibodies or antigen reactions. So biosensors are being used for any type of biological sensing of molecules. If something like a heart attack is being occurred for a person, in order to find whether it's an attack or any other thing, blood sample will be collected, and the serum will be examined for some type of antibodies present in that person. So that's how we can analyze each and every disease by examining the serum using biosensors. So it's very important in current scenario, and also it's a currently evolving field with a lot of applications.
Okay, thank you, sir. Thank you so much for your very informative and very helpful lecture. Okay, thank you, sir. Thank you very much.
Thank you once again, and it's a nice opportunity to interact with all of you. And you can just contact me through my mail ID. My official mail ID is achyuchandran@nist.res.in. So I will just put it as a comment here.
Sir, there is a request for many of the participants. Please share the PPT.
Yeah, that can be shared. Okay. So this is my mail ID which I have been shared here. So those who want the PPT, you can just mail me. I will get back to you. And if any questions or further discussion or any type of help is required, you can just drop a mail. Okay, I'll be back with you.
Thank you very much, sir. Thank you. Thank you, sir.
Thank
We are
you.
moving to the next session. Thank you, sir.
Thank you. Bye.
So we are moving to the next session. I welcome Dr. Pramila Kumari ma'am for the welcome speech for the second resource person.
Hello, can you hear me?
Yeah. Tell me, ma'am.
Welcome back to the second section of this webinar program. We have already informed you that the second section will be handled by Dr. Aravind K, Assistant Professor of SP College, Changanasheri. But I am very sorry to inform you that he is not in a position to attend the program due to some unavoidable circumstances. Today, we are very fortunate to have another distinguished scientist and academician, Dr. R.J. Krishnan, Associate Professor, Department of Physics, University of Kerala, Karyavattam, Trivandrum. Let me give a brief introduction of Dr. R.J. Krishnan. He is an academician and scientist with an advanced degree in material science research and development. He has proven track record of technical achievements in high technology area such as solar cells, thin films, laser spectroscopy, analytical instrumentation, imaging, cryogenics, and material characterization. He also have 12 years of experience in industry academic research and consultancy. He has achieved several prestigious awards like Kerala State Young Scientist Award, Certificate Award, Outstanding Contribution in Reviewing, elected as member of the Institute of Physics London, Teacher Summer Research Fellowship, and so on. He has completed 4 major projects funded by government agencies, and he has published more than 33 papers in various international journals. It is my pleasure and honor to welcome this eminent scientist and academician, Dr. R.J. Krishnan, to grace the program. Welcome you, sir.
Thank you, madam, for the wonderful introduction. I think there's a technical problem. My presentation on my screen is actually not available right now. Can you just handle that? Because I think I'm using my mobile right now. I would want to log in using my computer. I think the system administrator has to just accept my request for joining in.
Sir? Yes, sir.
Yeah.
Dr. Mira?
Yes, ma'am. Yes, ma'am. Please wait. Please wait some time.
Okay.
Yeah, hello. I think my
Okay, sir.
The slide
Okay,
is
sir.
clear.
Clear, sir. Clear,
yeah,
sir.
okay, but then
Okay.
yeah, okay, fine. Yeah, good afternoon to all of you. I think great opportunity given by Dr. Mira to me to give a presentation on this topic. Uh, Primarily, let me say that it has been a very short duration which I had to prepare this presentation. I hope I'll be able to deliver some justice to this. See, the title of my talk is Materials for Photovoltaic Devices. See, my area of specialization is photovoltaics. If you go to my next slide, you can see that I've picked up my outlines of what my presentation will be going through. Can you please go to the next slide? Meera madam, can you go to the next slide?
Mira?
Yeah.
Yes, sir.
See, the outline of my talk is I will be giving a brief introduction on photons, then an introduction to the crystals. Then I have 2 or 3 topics which I think are very basic at a fundamental level, just to make the understanding clear to the students and research scholars who are working in this area. Then I would be talking about a PN junction, which is basically for a photovoltaic device applications, and I would also show some of my experience that I have done. Okay, so if you go to the next slide. See, this is actually a simple question to some of the students I often ask. If you take the Google and ask the question to Google, what is the color of the sun? These are the images that come. So any student who actually looks into this image will be utterly confused about what is the actual color of the sun, because the images come in different colors and different shapes also. But even today, right now, I'm also not going to tell the answer, because Google will always give you a lot of different answers. It is left to you to decide what is the color of the sun. But then, what is the actual color of the sun? If you go to my next slide, the spectrum there represents the solar spectral radiation recorded from different levels. Say, at the top end, you can see the yellowish marking in the graph. This graph actually represents the solar radiation which is observed at the top of the atmosphere, whereas the red graph actually shows what is the solar radiation which is observed at sea level, whereas the black spectrum actually shows the actual black body radiation of the sun. Now, typically on the surface of the earth, if you look at the sun, we would find the sun to be yellowish red in color, right? So what does this mean? Supposing you want a material that works on the principle of utilizing the sun's energy, then you need to design materials which can actually work in this region, that is in the visible region of the spectrum. If you look at the spectrum, the visible region is between around say 400 nanometers to around 700 nanometers. Also, the spectrum also shows that the solar irradiance has the maximum irradiance in the range of around 530 to 540. What does that mean actually? It means that the solar irradiance is highest in the green region of the spectrum, whereas you have the energy distribution which is there throughout, say from 250 nanometers to 2500 nanometers. Now, looking at this, that is the sun, which is delivering a huge amount of energy. If you actually calculate the amount of energy which is radiant on the surface of the sun in a second, it is sufficient. If you can convert all that solar energy into electrical energy, it is sufficient to meet the demands of a state like Kerala for a day. For a 1 second, that is the amount of solar radiation which falls on the surface of the Earth for a second. If you are able to convert that into electrical energy, we will be able to meet the demands of the energy need of a state actually. But then that's all too much hypothetical. Now, if you want a device or you want a material which works on this, I have actually shown a simple calculation which shows that what would be the energy corresponding to each of these photons which is radiated on the surface of the sun. So if you look at this, look at violet as having a band gap of around 3 points, the energy level or the energy. See, a violet photon corresponds to energy of 3.07 electron volts, whereas the red photon corresponds to 1.96 electron volt. If you go to the next slide, I have shown some of the light sources that we have on available to us. Now, one of the most common light sources that we have is a halogen lamp. Meera madam, can you go to the next slide? See, the common halogen source, which is commonly used for testing any of the devices, is actually having the radiance from 400 to 800. This is very different to what the solar spectrum is. On the left-hand side, what you observe is the spectrum for a normal bulb which we use in our homes. Whereas at the bottom, what you see is the source from a handheld laser actually. So this is basically just to make you understand or to make the students understand that the light spectrum that we observe from different sources have a very different profile. And if you look at this particular profile, the energy which is being delivered to these sources is nothing close to what the sun is. So when we do experiments, we need something indicator which will be having a light very similar to that of the sun to actually make a test. That is why actually most of the journals, when you write papers, do ask, have you done a test using a solar simulator or what the light source was? Having a light source which replicates the sun is very essential in coming to a very good conclusion on your device. If you go to the next slide, I would start off with the basics of photovoltaics. The photovoltaic effect was actually first discovered in 1839 by the French physicist Edmond Becquerel. However, an actual device or the credit of making a device which works using this photovoltaic effect comes to or belongs to the British scientist William Grill Adams. Actually, Adams in 1876 discovered that crystalline selenium produces electricity when exposed to light. Now, his discovery in actually 1876 started off quantum mechanics. Actually, like that is where explanation had to be or quantum mechanics was required to find the solution why that such a material or why materials respond to radiation by producing a current. Now, if you go to the next slide, I would elaborate with a little more development on this technology. Where in 1883, it was Charles Edgar Fitts who actually constructed a solar cell using selenium. He actually marketed the light during those periods. However, it was in 1950s that actually a product could actually come into the market, but the product was based on silicon solar cells. In 1954, it was Chapin et al. Who reported a conversion efficiency of 6% for a single silicon solar cell with some bell lamps. If you go to the next slide, I would jump into some of the basics of understanding materials before going into device fabrication. Madam, if you can go to the next slide. So in general, materials are classified into crystalline materials, amorphous materials, and polycrystalline materials. If you look at the diagram, I think it is very clear that crystalline materials, you have a systematic arrangement of atoms. All these circles actually represent atoms in an ordered fashion. Whereas in an amorphous material, there is no ordering there. Whereas if you look at for a polycrystalline material, there is a local or a small range ordering. But when you go for material synthesis to make a device, you can use any of this. You can use a crystalline material, you can use an amorphous material, you can use a polycrystalline material for device fabrication. But the concept or the requirement is that any device that you make should be reliable, it should be cost effective, and it should be efficient also. So talking in terms of these three parameters of reliability, efficiency, and cost efficiency, there are a number of research groups who are working on multiple streams on developing different technologies. And today, I think silicon industry is the leader in this, because the silicon technology is well established. And in silicon itself, amorphous silicon as well as crystalline silicon solar cells are available in the market. Please, can you go to the next slide? This is just a slide to show what is the lattice point to my students here. See, a lattice point marked as A, B, C, and D. These are actually the lattice points and not Z. Just as a fundamental understanding. If you go to the next slide again, it's again a fundamental picture to show what a unit cell is. And you know that the arrangement of this, how you arrange the atoms would lead to a different, you have different types of crystal structures. Can you go to the next slide? Yeah. Now, in order to explain the photovoltaic effect, as I said, you need people, that is why quantum mechanics came into play. Now, there you had to look at the atomic level and the electronic level to explain why a photon, which actually is falling on a material, is resulting in flow of electrons into the material. For that, I think you can go to the next slide, where you would actually see I have actually drawn a picture of a sodium atom there. Now, the sodium atom is a typical example of one of the basic levels where you can understand on how or a material can actually become a conductor, because sodium is known to be a conductor, if you remember. If you look at the electronic configuration there, it has actually 14 electrons as 1s2, 2s2, 2p6. Now, to understand this, you have to think about the bottom diagram. That is, I've just simply drawn a structure showing where the core electrons are and the valence electrons are. Now, if you look into the core electrons, you can realize that the outermost shell for sodium actually is having only one single electron. Now, each of these states can contribute to each of these states can contribute to each of its electronic levels. That is what actually is shown in this picture. Now, if you go to the next diagram, what I have actually shown is that I have actually stacked up together a number of sodium atoms together. Can you go to the next slide? If you look at the next slide, I have actually placed 5 of these atoms together. Now, when you place 5 of these atoms together, I have drawn a picture showing what happens to the potential energy of this arrangement. So actually, where I'm coming to is I'm trying to come into one-dimensional periodic arrangement of having these atoms arranged linearly. Now, with each of these arrangements, what you can see is that the potential energy curves are arranged systematically in a one-dimensional periodic well arrangement. Can you go to the next slide?
Now, if you imagine that the electrons in the outermost shell or in the valence shell, they combine together, they can combine actually in two methods. We know that it can be actually in a symmetric or asymmetric fashion. Now, the picture here actually shows only the symmetric, but technically it is the antisymmetric combination that actually leads us, because when you do a symmetric combination of the two, it shows that the probability of finding out the electron is always there in space. Whereas if you go for an antisymmetric combination, there is a probability of not finding out the electron. That is the probability of not finding out the electron. Now, if you look at the bottom figure, it actually represents what is the change in the energy when two of these atoms are brought together. Now, if you go to my next slide, you can actually skip. Can you go to next? Can you go to next? Next. Yeah. Now, what I've actually done here is that if you imagine that an electron moves from one end to the next end, all these atomic waves will actually interact with each other when an electron moves from one end to the other end. When it moves from one end to the other end. Can you just move to the next slide? Now, what this slide actually shows is that when you have this periodic arrangement, these arrangement of these electronic shells actually overlap. Now, if you look at the bottom diagram there, what it is showing is that the 3s states and the 3p states of my sodium atom is actually interacting with each other, or it is actually overlapping with each other, which is actually marked with, if you look at the figure, you can see a lot of mesh type structure which has come up. So effectively what happens, the electron in the 3s state can very easily move to the 3p state without any energy itself. That is what actually is shown in the right hand side, where the 3s state actually works as a valence band and the 3p state actually works as a conduction band. So what happens in sodium, for sodium, it requires very little amount of energy to make it actually a conductor, because literally it requires no energy. If you look at this band overlapping, it requires no energy to travel. Hence, actually sodium works as a conductor. The idea that I want to give here is that as you arrange your atoms, the closer they come together, there's an optimum distance between the atomic arrangements when actually such band overlapping can be achieved, which makes the material, say it becomes a conductor, or it becomes a semiconductor, or it becomes an insulator. So it is actually how the bands get arranged based upon the technique that you use for material preparation. If you go to the next slide, I have actually shown two possibilities here. Like in the normal case, where classical mechanics, where we believe that the EK diagram is continuous, that is the energy K diagram, if you look at it, is a continuous diagram, whereas in quantum mechanics, we have to come to conclusion that the EK diagram is non-continuous. Now, this is actually a result of a lot of quantum mechanical calculations. But what we have to understand at this point, or what I want you to understand, is that the EK diagram is not continuous as we see on the left hand side, but it is what it is on the right hand side. Now, how did we come to this conclusion? I will spend 2 or 3 slides on explaining how this conclusion is coming to. Can you go to the next slide? Now, according to band theory, as I said earlier, if you arrange these atoms in a straight line, in a periodic fashion, it was Kronig and Penny who actually modeled that. Rather than imagining the potentials to be parabolic, let us imagine that they are actually square well potentials. So if you imagine that it is a square well potential, when you have atoms arranged linearly, what will happen in case it is a 3-dimensional model? But Kronig Penny actually worked only on a single 1-dimensional model. Now, according to their calculation, or they used actually our Schrodinger equation. That is where actually the Schrodinger equation was used to solve this. Where, if you go to the next slide, can you go to the next slide? They use the Schrodinger equation to solve for the energy of an electron in the potential well. Now, they came to 2 different conclusions actually. That is, it can be bound or it cannot be. It is either bound or it is free. Now, if you put the model as it is a bound model, you would actually end up with, if you go to the, can you go to the next slide? When you go with the bound model, what you find is that it is the potential functions are symmetric in every potential well, which means any of the wells, the energy and the wave function is actually symmetric. So there is a flow in symmetry as you go from one well to the other. This is what actually the block function actually comes into play. Now, if you go to the next slide, further solving the Schrodinger equation, they came up with a relation which says that the lattice, that is K, the A is actually the lattice. The lattice should be actually a fundamental multiple of, say, pi. Now, if you go to the next slide, this relation that based on Schrodinger equation, the energy diagram to be non-discontinuous results in either, if you imagine that the electron is completely free, you're bound to get only a continuous EK diagram. But if the electron is bound, the energy is not, the electron is not completely free, which means that the energy is not continuous, but it is discontinuous. This is what actually the diagram at the bottom actually shows, showing that whenever the Ka, wherever the Ka is equal to plus or minus n pi, this wherever Ka is equal to plus or minus n pi, you have actually the energy is discontinuous. That is where actually the band breaking takes place. Now, if you go to the next slide, the probability distribution function is calculated on finding out where the possibility of the existence of an electron is there. This diagram is actually not very correct, because basically, according to Cronin and Payne model, that is where actually there were certain regions where the probability was 0, and there were regions where the probability was greater than 0. So all such regions where the probability was 0 actually is where we say that it is the band gap exists. Can you go to the next slide? The next slide. If you come to this slide, actually, what is drawn here is that you can see that there are multiple band bendings in this. Can you just click once more? Just click once more. Yeah, this is just to say that, see, as the number of states, if you look at the left side, you have 1s, 2s, 2p, 3s. As you keep on going up, you have more and more states, and as the density of electrons increases, the states actually, from being single valued energy states, they end up being continuous energy valued states. That is where the figure, if you look at the figure, you can find that there are a large number of energy states within each of these states. Now, what does this mean? If you put n number of atoms together, every of these states are going to interact with each other, and they would result in a large number of breakings in our EK diagram. Because of this, what you have to understand is that in a material, we speak about having a band gap. But in every material, it is not a single band gap, but there can be n number of band gaps. But theoretically, the lowest difference in energy between any of these two bands is what we assign to be the band gap of that particular material. Why I'm stressing to this point is that when we go for a photovoltaic device, you need to have the energy band gap of the material which matches with that of the solar radiation. As I said, if you look at the solar radiation, the visible spectrum is where the maximum amount of irradiance is. So you need to have a material who has a band gap which matches the solar radiance, or it should be a material which can actually absorb maximum amount of solar radiation, or which means that we have to speak about a material which can absorb all the visible radiation. Now, why is that? So because photovoltaic effect is basically a material in which it absorbs the photon and converts the photon into a current, or the photon actually produces a current flow in the material which can be used as a battery. So this picture, what I want to stress here is that you can have multiple band gaps in a material provided you play with the density of states, which means if you can play with the doping of the material, you can change the band gap of the material. If you can change the size of the material, again you are changing the band gap of the material. So there are different possibilities of how you can engineer a material to suit your need. Can you go to the next slide? Yeah, this slide is just to show that what happens to materials. Like you have binary compounds. I've only shown binary compounds here. showing that how the variation in band gap takes place as the change in lattice constants of these materials take place. Now, ideally, as I said, we have silicon is the one of the leaders today in photovoltaic industry with around the lattice constant is around 5.3 here with a band gap of 1.09. Now, the question can come as silicon has a band gap of 1.09 and still why do you claim it to be the best material? I'll come to that later on. Can you go to the next slide? Here, I think I'll be following 3 to 4 slides, with basically only for the research scholars, just for basic understanding. As I was saying earlier, see, sodium is said to be a conductor. Now, why is that? It is basically because of the overlapping between the 3s and 3p bands. The 3s and 3p bands overlap, because of which the electron is able to freely flow from one level to the next level. If you go to my next slide, I've shown the difference between between a semiconductor, a conductor, insulator, how the bands are aligned at 300 Kelvin. Now, sodium chloride or our common salt. Now, common salt is an insulator with a band gap of 2 electron volt. Because now, normally you will have a doubt like semiconductors have a band gap up to say around 3.3 electron volt. Now, so most of the students say a band gap of 3.3 electron volt means it has to be a semiconductor. No, see, sodium chloride, the band gap of 2 electron volt is still an insulator. So why is that? It is basically because of how the bands get overlapped in the material. I just wanted to stress that point there. That is why I put up this slide. Can you go to the next slide? Can you go to the next slide, madam? Yeah. Here, see, silicon, it has a atomic density of around 5 into 10 raised to 22 atoms per centimeter cube. Now, why is this very specific? Basically, if you go into the density of states calculation, fundamentally, you have to remember that the total charge N is actually the product of N and P, where N and P here represents the N doping level and P represents the P doping level. So any kind of doping that you do cannot overcome this density or total density of N. Now, silicon, which is actually covalently bonded, it is very easy to dope it. So either to be P-type or N-type. That we do it at, say, from 12th standard, I think we teach students what happens when you do doping into your silicon. Can you go to the next slide? Can you just give one more? Can you just keep tapping there? I want the entire slide. Yeah, correct. So, in order to change the density of states in silicon, you can do doping, which can be actually pentavalent doping or a trivalent doping to convert either to be a P-type or N-type. Now, but fundamentally, as I earlier said, you can change N or P, but you cannot change the total density of N, capital N there. So when you design a material, the role of doping is actually in order to control the mobility in the material as well as the carrier lifetime. Now, one of the most essential properties or one of the most essential fundamental requirement for a photovoltaic device is that the carrier lifetime should be very large. Now, why is that? It is basically because, see, when a photon comes and falls on a material, now when a photon falls on the material, the photon is to break into an electron and hole. Once it splits into an electron and hole, it should not recombine, which means they should sustain themselves as an electron and hole. That is, they should remain separated. Like I normally say that, see, when you get married, you have a husband and wife. So for a child, it is easier to extract something from the parents when both of them are split apart. If the father and mother are together, it is not easy for a child to take anything from them. But if the father and mother are separated, from each of them he can earn some amount of pocket money.
Sir, hello? Hello? Hello?
ஹலோ மேம், அவரோட நெட்வொர்க் கட் ஆயிருக்கு. மேம் மேம் கேன் யூ ஹியர்? மேம் ஹலோ.
Hello, sir. Hello, hello.
எஸ் மேம், அவரோட நெட்வொர்க் கட் ஆயிருக்கு மேம். நெட்வொர்க் வர மாட்டேங்குது அவரோட.
Okay, yes, yes, sir, yes, sir, yes.
நெட்வொர்க் வரல. அவரு ரீஜாயின் பண்ணதுக்கு அப்புறம் ஆப்ரேட் பண்ணலாம் மேம். மேம் அவருக்கு ஃபோன் பண்ணி ரீஜாயின் பண்ண சொல்லுங்க மேம்.
Okay, sir, welcome back. Jai Krishnan, sir. Jai Krishnan, sir.
Ma'am, he is not there, I think. What is the slide number?
Okay, he has some network problem. He'll be back soon. Hello, sir. Hello, sir.
Ma'am.
Okay, okay.
Sir came. Okay, ma'am.
Okay, sir. Okay, sir.
Okay.
I don't know which slide actually my network crashed.
I think it is 35, sir.
Can you, that's
35.
35, sir. 35.
35. I think your slide number and my slide number, there's a confusion, I guess.
Okay, sir. This one.
Can you just upload your from your end?
What, sir?
Can you present the PPT?
Yeah, I'm presenting, sir. Let me present. Is it okay, sir?
Summary of charts. Okay. Yeah, okay.
Okay, sir?
Yeah, fine.
Yeah, thank you.
See, basically what we are talking is, since silicon, you can actually dope it to be either P-type or N-type based on the type of token that you're going to use. I think I'll move a little bit further. Like, see, if you want to do N-type of doping, it has to be a pentavalent doping, whereas if it is P-type, it has to be a trivalent doping. Now, whatever be the kind of doping, what I want to stress is that this total charge density, N, capital N, small n would always be a constant. So, you may increase the N doping density so after 10 to 15% millimeter cube, and your P doping density to say around 10 to 15% millimeter cube. But there will be always a balance between the two. Can you go to the next slide?
Sir, excuse me, sir. Sir, excuse
Audio
me, sir.
not clear. Audio
Yeah,
not
yeah.
clear.
Yeah, others are asked to switch off your microphone. Then only it will be clear.
Participants, please mute your audio
Microphone.
and video, please. Okay, sir. Continue, sir. Please. Continue,
Yeah,
sir.
am I audible?
Yeah.
I'm audible.
Yeah.
Okay. See, what I was saying is that if you look at silicon as a case, you can dope both as P-type or N-type based on the kind of dopant that you involve. You can actually use a pentavalent to make it N-type or a trivalent to make it P-type. And the total concentration would always remain a constant. That is, the N and P, that is N dopant and the P dopant concentration will play a balance so that the total density of states will be at in a 10 raised to 22 always. Yeah, the next slide. Can you go to the next slide? So in this, I think I'm moving a little bit deeper into my topic here. What I wanted to show in this presentation is that, see, what is optical absorption? So when light falls on a particular material, we anticipate that the electron from the valence band moves to the conduction band. So an incoming photon is to be converted into an electron and hole pair. Now this can happen in in all kinds of materials, provided the incident photon has sufficient energy to push it from the valence band to conduction band. What you see here in this figure is the what is called as direct band gap materials, in which the minimum of the conduction band and the maximum valence band have the same K value. In such cases, there is no requirement for change in momentum for an incident photon. Can you just click once more? In the next diagram, when you see something which is called as a indirect band gap material, where for an electron or for a photon to be converted into an electron and hole pair in such materials, there has to be a change in momentum. Such kind of materials are actually called as indirect materials. So you can make a device using both kinds of material, that is a direct material, a direct band gap material, or an indirect band gap material. But the problem would be that since there is a change in momentum for an indirect material, there will be problems like heating effect will be very high. That is, such materials may not live for very long. They would die, or they would actually get destroyed. So when you go for a device level, it is always preferable to go for direct band gap materials for device fabrication. Yeah, the next slide. Now, in this slide, I've just shown what is a solar cell. If you see, it is very clear that what is clear that the photon is coming, it is falling on the P side of a junction, or say a junction which is made up of a P material and N material you are seeing in this diagram. The photon comes and falls on the P-type material. It pushes the electron from the P side to the N side. Madam, if you just hit back and forward, the video will play once more, just to make the listeners understand. Hit back and then hit forward on the key. So what is happening, I'll repeat. A photon, when it falls on the P-type material, pushes the electron from the P side to the N side. So this is very interesting. Why? In a P-type material, the electron is actually a minority carrier, whereas in the P-type material, the hole is the majority carrier. So in this diagram, what I want you to understand very clearly is that a solar cell is a minority carrier device. Now, why do I use the term minority carrier device? It's basically because the photon is actually pushing the electron, which is the minority in the P side, to the N side. And if you further look in the N side, what is happening is that when the electrons from the P side reach the N side, they actually are, say, basically current is the flow of electrons, right? So this coming in electron would actually push electrons from the N side outwards. They push the electrons from the N side of the material, producing a voltage. So basically, solar cell is also a battery. You can call it to be a battery basically whenever the sunlight is falling on this material. I hope that idea is very clear. Yeah, the next slide. Can you go to the next slide? Can you go to the next slide, madam? Hello? I think there is some network problem. Can you go to the next slide, madam?
Mira? Hello, Mira?
Sir, yes, sir. Some problem, sir. Wait, please.
Yeah.
Few minutes.
Okay, I think I will manage without these slides coming in. See, in the next slide, I actually am showing the same thing only. What is being shown is that when light falls on this PN junction, the photon which is incident on the P side will actually cause an electron hole pair to be created across the PN junction. That is where again we have to understand what should happen is basically the electron hole pair which is generated because of optical absorption should be pulled outside. Now that is where actually you need to have a little bit of engineering concept which come into device fabrication. Remember, light falls on the material. On the P side, the electron is pushed inwards. So what should happen? You have holes on the P side, and to make it mobile, you need to pull the hole outwards. So you need to have a hole transporting layer there. Now on the N side, when the electron is pushed that side, now you need the electron to be pulled out, which means you need to have an electron transporting material. Now, as research is developing, you have a lot of, I'm speaking relating to silicon, but there are other technologies which are currently available, like the perovskite solar cell is there, the dye-sensitized solar cells are there. Any of these solar cells that you speak about, fundamentally what we need to understand is that you need to have structures, or you need to have materials which can actually facilitate the movement of the electron and hole in opposite directions. So in order to do that, the material should have very high mobility also. Now, to have very high mobility, the band diagram, you have to understand that the bands shouldn't, or the bands should be in such a way that the electrons move without creation of any phonons.